Many laboratories work with solid lipid nanoparticles, or SLNs. These tiny particles hold great promise for delivering drugs and other applications. A common challenge arises after their creation. The nanoparticles are often too dilute. They exist in a large volume of liquid. To be useful, they must be concentrated. This means increasing the number of particles in a smaller, more manageable volume of solvent. This step is crucial for research, testing, and eventual use in products. Without effective concentration, much of the potential remains locked away in overly diluted solutions. The standard tool for this job is often an ultracentrifuge. This powerful machine spins samples at incredibly high speeds. The immense force it generates pushes the heavier nanoparticles to the bottom of a tube. The lighter liquid can then be carefully removed. But this solution is not available to everyone. Ultracentrifuges are expensive. They take up significant space. They require specialized training and maintenance. For many smaller labs, academic settings, or early-stage startups, owning such a machine is simply not feasible. The absence of this single piece of equipment can feel like a major roadblock. This situation forces scientists to seek alternative methods. The goal remains the same. They need to concentrate their SLNs, but they must do so using tools that are more accessible and affordable. Well, that sums up the challenge and the direction researchers take. One of the most straightforward concepts for concentrating nanoparticles is gentle evaporation. The basic idea is simple. You encourage the solvent, often water, to slowly turn into a gas and leave the sample. As the liquid volume decreases, nanoparticle concentration naturally increases. A sample might be left under a gentle stream of an inert gas like nitrogen. This flow carries away evaporated solvent molecules. Another approach uses a rotary evaporator under a mild vacuum. That lowers the solvent's boiling point and speeds the process without excessive heat. The success of this method hinges on one critical word: gentle. Heat speeds evaporation. But for SLNs, too much heat can be disastrous. Lipid-based particles are sensitive to temperature. High heat can cause them to melt, change shape, lose their structure. This would render them useless. If evaporation is too quick, it creates turbulence in the liquid. Turbulence forces particles to collide and stick, aggregation. The key is a slow, controlled rate of solvent removal to avoid these forces. This technique is best for moderate concentration steps. It's a relatively simple setup found in many labs. It works well for initial concentration steps. However, it has limits. As nanoparticle concentration increases, clumping risk rises. Pushing concentration too high with evaporation alone can make an unstable product. It's also not selective. Non-volatile components, salts, other solutes, also concentrate. So, view gentle evaporation as a useful tool with a specific operating window. Another powerful strategy involves causing the nanoparticles to separate from the solution. This can be achieved through selective precipitation. Subtly change the chemical environment of the liquid. The nanoparticles become less soluble. They begin to fall out of the solution as a solid. Sometimes this is done by adding a specific salt, or by adding another solvent the particles do not dissolve in. Once precipitated, the particles can be separated from the bulk liquid. The liquid is decanted or pipetted off, leaving a concentrated nanoparticle mass. That mass can be resuspended in a smaller volume of fresh solvent. This requires deep understanding of the nanoparticle's surface chemistry. Stability depends on a delicate balance of forces. Introducing a new substance can disrupt that balance. The trick: do it in a controlled, reversible way. A major risk is irreversible aggregation. If particles clump too tightly, they may never redisperse. So the technique must be optimized for each nanoparticle type. A related but distinct approach is tangential flow filtration, also known as cross-flow filtration. It uses a membrane with pores of a specific size. The suspension is pumped to flow across the membrane surface. Liquid and small molecules pass through the pores. Larger nanoparticles are retained and returned to the main container. TFF minimizes clogging and is gentle. Dialysis offers another gentle and effective path to concentration. This technique also employs a semi-permeable membrane. The nanoparticle suspension is placed inside a bag or cassette made of this membrane material. This bag is then submerged in a large volume of a different solution, known as the dialysate. The membrane has tiny pores. These pores are large enough to let small molecules like water, salts, residual solvents pass through, but they are too small for the much larger nanoparticles to escape. Over time, the small molecules diffuse across the membrane, moving from an area of higher concentration to lower concentration. This process can be cleverly adapted for concentration. If the external solution is a polymer that attracts water, such as polyethylene glycol, it can draw water out of the dialysis bag. This process is called osmotic concentration. The large polymer molecules in the dialysate cannot enter the bag, but they create an osmotic pressure that pulls the smaller water molecules out. As water leaves the bag, the volume of the nanoparticle suspension inside decreases, and the nanoparticles become more and more concentrated. This method is exceptionally gentle, as it involves no mechanical stress or harsh chemical additives inside the sample itself. The primary limitation of dialysis is time. Diffusion is a slow, passive process. Concentrating a sample using this method can take many hours or even days, depending on volume and target concentration. The setup is relatively simple, but the process must be monitored to ensure it does not proceed too far, which could lead to excessive concentration and potential particle aggregation. It is an excellent choice for delicate samples where preserving particle integrity is the absolute highest priority and speed is not a major concern. A related concept is solvent exchange, which can be a precursor to concentration. Sometimes, nanoparticles are made in a solvent that is difficult to remove, such as an organic solvent with a high boiling point. Using dialysis or tangential flow filtration, this initial solvent can be gradually replaced with a more desirable one, like water. Once the nanoparticles are safely transferred into the new solvent, other concentration methods, such as gentle evaporation, become much easier to perform. This two-step process provides a high degree of control over the final composition and concentration of the nanoparticle formulation, making it a versatile strategy in the researcher's toolkit. Regardless of which alternative method you consider, the journey should always begin with small-scale tests. Before committing a large, precious batch of nanoparticles to a new procedure, experiment with a tiny fraction of it. Take a small aliquot and apply the chosen technique. Observe the results closely. Does the solution remain uniform? Does it become cloudy, indicating aggregation? Are flakes or sediments forming at the bottom of the container? These visual cues are your first and most important signs. Keep detailed records during these tests, essential for success. For each experiment, write down everything. Note the starting volume and appearance. Document exact parameters: temperature, rate of gas flow, type of membrane. Record the final volume and appearance of the concentrated sample. This note-taking creates a roadmap. It lets you reproduce successful results and helps you troubleshoot failed attempts. Without a clear record, you are guessing and you may repeat the same mistakes. Seek knowledge from those around you. Your lab or institution is a community of experts. Talk to experienced colleagues. Ask a senior researcher in your group. Ask a neighboring lab. They may have practical tips not in textbooks. Their experience can save time and resources. Science is collaborative. A simple conversation can illuminate the path faster than solitary struggle. Vendors and manufacturers are valuable resources. Contact the company that supplied your lipids. Contact the company that supplied your surfactants. They may have application notes or technical specialists. They have a vested interest in your success. Manufacturers of filtration equipment can advise. Manufacturers of dialysis equipment can advise. When you reach the limits of your expertise, especially when planning to scale up, consult an expert. By proceeding with caution, testing methodically, and asking for help, you can successfully concentrate your nanoparticles and advance your research.